Imagine operating a distillation column in a chemical plant. The column successfully produces the desired product purity, but every hour it consumes a significant amount of energy through its condenser and reboiler. Now, consider this question. Can the same separation be achieved while consuming substantially less energy? Yeah, distillation is one of the most energy intensive operations in the chemical process industry, accounting for a large fraction of total plant utility consumption. Even small improvements in operating conditions can translate into major reduction in energy cost, carbon emissions, and environmental impact. So, in this project, I investigated how the feed tray location, reflux ratio, and number of stages affect the performance and energy consumption of a binary distillation column. Starting from the classical McCabe-Thiele Design method, I extended the analysis using UniSim Design simulations and developed a MATLAB-based optimization tool to identify energy-efficient operating conditions and quantify their sustainability benefits. Chapter 1. Designing the distillation column using McCabe-Thiele Method. The goal here is to develop an initial column design before simulation. So I used McCabe-Thiele graphical method for separation of a benzene-toluene mixture, where benzene being more volatile component. The column is designed for the purity demand from the customer for 0.99 distillate benzene mole fraction while maintaining benzene mole fraction of 0.01 in bottoms product. So we'll have to consider a few assumptions, alright? The feed entering the column is at its bubble point temperature, that is 92.4 degrees Celsius, which means Q equal to 1. That's a vertical line. What do you mean by Q? So Q is a fraction of liquid in the feed entering the column. So suppose if there is 100% liquid entering the column, then the Q value equal to 1. And if there is 90% of liquid and 10% of vapor present in the feed, then the Q value becomes 0.9. Okay, that's one assumption. And moving to the next one, which is equimolar flow. That means the feed mole fraction is 0.5. And we are doing all this in steady state operation. And it's a binary separation system. There is constant molar overflow in both rectifying and stripping section. There is negligible heat losses to the surrounding, constant pressure throughout the column, and equilibrium established on every theoretical stage, total condenser and partial reboiler assumptions. So I sourced the VLE data for benzene toluene from commonly used chemical engineering design and distillation analysis. And based on that data, I have plotted the graph. So this is the VLE data I was talking about, where X is the mole fraction of benzene in liquid and Y is the mole fraction of benzene in vapor. And we plot this on the graph and we get the equilibrium curve and we join 0, 0 and 1, 1. And this is the diagonal. Alright. Now we set XD, XF and XP on this diagonal line. XD is 0.99 because the customer wants 99% pure benzene. That's why mole fraction of benzene in distillate is 0.99 and mole fraction of benzene in the bottoms is 0.01. This is not significant. Our goal is 0.99. Alright, because we want 99% pure benzene coming out from the distillate. Alright, and then mole fraction of benzene in feed is 0.5. I told you, no, it's the equimolar condition. Alright, and then we draw the Q line, and this Q line is equal to 1 because the feed is at its bubble point. And now the intersection of this straight line and the equilibrium curve gives us the pinch point. Now what you do is, starting from XT, draw a straight line passing through pinch point and it should intersect with the y-axis. And this gives you the y-intercept as 0.44, which is substituted in this equation over here, which is XT by R minimum plus 1. Okay? And you may ask, what is R minimum? R minimum is minimum reflux ratio, wherein there is infinite number of trays in the column. And obviously that's not feasible and not possible to have infinite number of trays or large number of trays because it's more operating cost and too much finance, too much money, too much investment and all of that. Yeah. So obviously we can't operate a column at R minimum. So what we do is we always consider for the industrial design as R actual is 0.5 times of R minimum. Alright, so R actual is equal to 1.875. Yeah, and using this R actual value, we substitute it in the ROL equation which I was talking about for the rectification. That's the rectification section, and you get XD by R plus 1 equal to 0.99 by 2.875, which is 0.3443, I believe. Yeah, that's what I have done. But yeah, and then what you do is you mark it on the graph, on the y-axis, I mean, and then from this point join it to the XD. So you join this, and wherever it touches the Q line, just mark it. All right. So once that's done, you join this point and the XP, this point and the XP, and this will give you the stripping operating line. So we have rectifying operating line and stripping operating line. All right. Now what you do is you start drawing the number of stages, which is from this XT, and you keep going. It should touch, the moment it touches the equilibrium curve, you just get it vertically down, horizontal, and you get it vertically down, and you keep doing it. And once you cross this point, you continue it. You make sure you touch the equilibrium curve, and then it should go down till it touches the SOL, stripping operating line. And keep doing it, and the moment you cross XB, that you stop the number of stages. Okay, and from all this, I got to know that the feed tray is the 6th tray, and there are total number of 16 identical trays for R equal to 1.875. So this is the entire graph, just to give you guys an idea. Also, another point, there are no side streams and there are no multiple feed. Okay, this method only provides an initial estimate of the column configuration. It does not predict condenser duty, reboiler duty, or overall energy consumption. So the next step was to develop a rigorous steady state simulation in UniSim Design and evaluate the column's performance from both separation and energy perspectives. Moving to chapter 2, process simulation in UniSim Design. Yeah, coming to the UniSim, this is the process flow diagram. Here is the feed in, and the composition, like I said, it's set at 0.5 mole fraction. And it's set in mole fractions. Okay, and moving to conditions, set it at 100 molar flow, and the temperature is set at 92.4, and pressure is 1 atmosphere. Yeah, and this is the column. The feed tray is 13th tray, and there are total of 23 trays. All right, the feed tray location is changed and the total number of stages is different, because in a real column it does not operate at 100% efficiency. So we have assumed that the column is operating at around 70% efficiency. That's why the total number of stages changed from 16 to 23, and the feed tray location changed from 6 to 13. Performance, you can get a lot of information from this. Condenser duty and the reboiler duty is right here. Yeah, if you go to summary, you can get a lot of information. This is the flow sheet, and yeah, there is a lot over here as well. So going to monitor temperature profile, pressure profile, flows profile. You can get every single data from this. Yeah, moving to the data book. Everything is dependent except for the distillation column. Okay. When I go to case study, and here is the Excel that I have built. Stages, feed tray, reflux ratio, XT, XB, condenser, and reboiler duty. This is for multiple trials. All right. 1 second, let me just set it in kilowatt. Yeah. So yeah, coming to this, I'll explain this in a bit. In case study, in case study, I go to view. I've set the lower bound as 7 and higher bound as 13 with increment of 1. So it'll go 7, 8, 9, 10, 11, 12, 13 trays. And I can set the reflux ratio as 2, hit run. And I go to worksheet just to get, and this is the composition of distillate and bottoms. So this is the condenser duty for that reflux ratio and reboiler duty. Okay, now coming back to the data book, I can hit start and I can go to results. And here I'll get all the data for 7, 8, 9, 10, 11, 12, 13 feed tray. And I get the respective condenser duty and reboiler duty. And I go paste it over here. And I can just, do this. Put it here. And this is for reflux ratio equal to 2. Bottoms, and this is the energy duty. Alright, so once this is done, let me just change the units because I want it in kilowatt and not kilojoule per hour. Hold on. It should be somewhere here, yeah, kilowatt. Yes, that's done. Let me just save it. This should make it easy. It should be in kilowatt. Yeah, that's cool. All right, moving on. So we did it for if R equal to 2. Now we change it to R equal to 2.1. And for this reflux ratio, we try it with different feed tray location. Like I said, for 7, 8, 9, 10, 11, 12, 13. Hold on. Yes. So, 7, 8, 9, 10, 11, 12, 13. I hit start. I get the results. And for these feed locations, I get the respective condenser duty and reboiler duty for R equal to 2.1. Same thing, I just copy it and then I paste it and then I move to 2.2, hit run. And then I get the results from it. I go here, click start, get the results. And then same thing, I just copy and go paste it in my data set, which is in the Excel. One second, let me just, this is the graph. And let me just transpose the table so that's easy. So I just copy this. And I just paste it over here. Yes, that's it. And what I do is I keep repeating this till I reach the 7th tray XD value as 0.99. At R equal to 3.2, for the 7th feed tray, the XD was 0.99. That's when I stopped doing the iteration and I end it with R equal to 3.2. Once that's done, now we try to optimize it, whether this is feasible or not. Chapter 3, Sensitivity Analysis and Data Generation. So the objective was to identify operating conditions that satisfied the required purity specifications while minimizing energy consumption. So for each feed tray location, the reflux ratio was adjusted until desired product purity was achieved. And this was repeated for multiple tray location. And this data set formed the basis for the optimization study. So here is the data set I was talking about. There are about 120 runs and it has different stages: feed tray, reflux ratio, XT, XP, condenser duty, reboiler duty. And this feasible column talks about whether that particular trial has met the purity level or not. So here is the formula. And if it satisfies this condition, it's a yes. And if it does not, it's a no. And I've taken all the yes values and put it in a different sheet, and this is the final data set. And I've mentioned number of feasible runs 76, number of non-feasible runs 44, and total number of runs 120. And what I've done is I've saved this file and I've imported it to MATLAB. So obviously with the help of Claude, I've generated graphs for energy purity, heat map, reboiler duty versus feed tray, and feasible region map. So I'll show you the graphs. Yeah, so this is the first graph, the second graph, third graph, fourth graph, fifth graph. I'll be explaining these graphs one by one. First graph is distillate purity versus feed tray location. This graph shows that distillate purity changes when the feed tray location is moved within the column. We can see that purity generally improves as the feed tray is moved closer to tray 13. So higher reflux ratios also result in better separation and higher product purity. Second graph is energy purity trade-off plot. This graph compares product purity with the energy required for separation. It shows the typical trade-off in distillation, that is, achieving higher purity usually requires more energy. The highlighted optimum point gives the required purity while keeping energy consumption as low as possible. Third graph is reboiler duty versus feed tray location. This graph shows the effect of feed tray location on reboiler duty. As the feed tray is moved through the column, the energy requirement changes. The lower reboiler duty occurs near tray 13, which indicates a more energy efficient operation. Coming to the fourth graph, that is reboiler duty contour plot. This contour plot combines the effect of feed tray location and reflux ratio. The colors represent different levels of reboiler duty. Darker regions correspond to lower energy consumption, while lighter regions indicate higher energy usage. It helps visualize where the most energy efficient operating region exists. Coming to the fifth graph, that is feasible region map. This graph separates operating conditions into feasible and infeasible regions based on the required purity specifications. The blue region contains all the operating conditions that meet the desired product purity, while the gray region does not. The optimum point lies within the feasible region and represents the best balance between purity and energy consumption. These plots helped me understand how feed tray location and reflux ratio influence both product purity and energy consumption, allowing me to identify the optimum operating condition as feed tray 13 and reflux ratio as 1.9 for efficient column operation. After identifying the optimum operating condition, I wanted to understand its environmental and economic impact in addition to energy savings. So here is the base case versus optimum spec scenario. So this is what I have done. So reduction in total duty was this much, and we assume that the column operates for 8,000 hours per year, that is continuous industrial operation, and annual energy saved is this into this, which gives me this value, and we assume the emission factor as 0.2 kg CO2 per kilowatt hour. Alright, and therefore annual reduction in CO2 emission is 0.2 kg CO2 per kilowatt hour into annual energy saved, which is this. So we get about 3,258 tons of CO2 prevented. Okay, CO2 emission prevented. We know 1 carbon credit is equal to 1 ton CO2 reduced. So the company generated about 3,258.3263 carbon credits. So if the value of 1 carbon credit is rupees 1,000, company has holdings worth this into 1,000 number of carbon credits into the value of it, which comes out to be around 32,58,326 rupees. So this they can either sell or keep it. I developed a MATLAB App Designer tool called the Distillation Column Energy Optimizer. Before that, I built this Excel file which has all the data and condenser duty, reboiler duty, and total duty mentioned. So what I did is I imported this file to MATLAB, and I have this app ready, and the code I got with the help of Claude. And so I can set the number of stages, feed tray, reflux ratio, and 16, 6, and 4.3 is the base case. So I've set that, and I can check the duty for selected specs, condenser duty, reboiler duty, and total duty. This is the percentage total energy saved versus switching to the optimum spec. Optimum spec was 23, 13, and 1.9. And environmental and financial impact, I'm annually saving about this much. CO2 reduction is about 3,200, and carbon credits, and everything is given in this. So I can play around with different feed tray. I'll set it maybe 12 and maybe 11, and I can select any reflex ratio, and it'll give me the total energy saved against the optimum spec. So 22.82%. This is the total duty, and this is the annual estimated carbon credit value in rupees and US dollar. So now I would let's say 10, and you can choose any reflex ratio over here. Okay, let's go with 3, and 28.92, and this is how much money I've saved, and that's in US dollar. So in this project, I combined the McCabe-Thiele method, UniSim process simulation, and MATLAB to optimize the operation of a binary distillation column. I studied the effect of feed tray location, reflex ratio, and number of stages. An optimum operating condition of 23 stages, feed tray 13, and reflex ratio 1.9 was identified. This reduced the total column duty from 4,323.6 kilowatt to 2,287.2 kilowatt, resulting in approximately 47% energy savings while maintaining the required product purity. To make the results more practical and accessible, I developed a MATLAB App Designer tool that allows user to select different operating conditions and instantly view the corresponding condenser duty, reboiler duty, total duty, energy savings, CO2 reduction, carbon credits, and estimate carbon credit value. The analysis showed that optimizing distillation column operation not only reduces energy consumption and emissions, but can also provide potential annual financial benefits through carbon credit generation. So talking about the future scope, future work can focus on let's say reducing some of the assumptions made in the study by incorporating real plant data, more rigorous thermodynamic models, and dynamic process behavior. The application can also be expanded to include advanced optimization techniques and real-time sustainability analysis. I'll share all the Excel files, all the graphs, and the MATLAB app as well in the description. Maybe you guys can experiment, check it out, do trial and error, and let me know how it goes, alright? So, all the best. Take care. Bye-bye.